Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this, we're gonna see problem number 3, which is, if you don't know, the hardest problem of today's contest. Problem 4 is already live. If you know why it was hard and what you should make sure that you never miss on in OAs, do make sure to watch this video. Short link in description and comment section. Now, before you start off, just bear with me. Whatever I explain, ultimately in the end, you will know what it is. Now, it simply says that you are given an array of nums consisting of positive integer. As you can see, I am given nums. Now, a special subsequence is defined as a subsequence of length 4. Now, if you don't know, a subsequence is that if I choose some elements in any gap whatsoever, but these elements should be ordered. As in, like, okay, I choose this, then this, then this, and then this. Okay, and they are given, okay, I will choose at index P, Q, R, and S, where obviously P is less than Q, less than R, less than S. Okay, now this is the condition the subsequence must satisfy. Again, the condition is nums of P into nums of R is equals to nums of Q into nums of S. And also, there is one more condition that these P, Q, R, and S should also follow the condition of that Q minus P. As you can see, I simply showed the very first case that I have a P, Q, R, and S. This is the base case. Kind of, that Q minus P should be more than 1, which means Q minus P should be more than equal to 2. Same way, R minus Q should be more than 1, which is R minus Q should be more than equal to 2. And same way, S minus R should be more than 1, which is S minus R should be more than equal to 2. Now, again, they have mentioned what a subsequence is. The ultimate maqsad or the primary aim for us to find the number of different special subsequences in nums, which is all the possibilities. Now, in this case, if we go ahead and try the very basic brute force approach, which is try for all possible P. For every P, go and try for all possible Q. For every Q, go and try for all possible R. For every R, go and try for all possible S. So for one P, n possible Qs, n possible Rs, n possible S. For every P, which means n possible Ps, I have a complexity of O of n to the power 4, which will obviously not work. And the biggest hint of this problem itself is the time constraint, which lets us know that we have to transform it to O of n square or maybe O of n square log n as the maximum complexity, nothing more than that. Now, this is the ultimate thing from which we will start off, which means that rather than choosing 4 indexes, I have to choose 2 indexes. And obviously, when I choose 2 indexes, I can apply a for loop in those 2 indexes. That is my ultimate aim, and what I'm trying to do here is, because I want, rather than choosing 4 indexes in the for loop, I will choose 2 indexes because that's what I can do. Now, obviously, I cannot choose P or Q, because if I choose P or Q in the for loop, then I will have to try for R and S again, which will again give O of n to the power 4. So I thought of, okay, let's choose P and R. If I choose P and R, which means, okay, I will try in the for loop. Again, in my for loop, I will try for PR, or maybe you can say RP, anything. Okay, I will try this thing. Okay, which means that I will be using 2 for loops here, and I will fix P and R. If you see that R is kind of, again, when I say for loop, I will have a for loop specifically taking P and R as the driving factor. So I will, let's say, take R and P as a driving factor in my 2 for loops. When I say R as a driving factor, I realize that R value can go from what? Obviously, we showed that R value will start off from 4 and ultimately will go in the very end. Considering my n was 7 in this case, it can go up till n minus, I should say, n minus 2, less than n minus 2. So my R can go from 4 to up to n minus 2. Considering in the very end, I will put up S. Again, I will show you that how we can check what S can be, but this is the possible values of R. That R can start off from 4 and end up till n minus 2 less than. So, okay, I figure out what R can be. Again, I'm not saying this is the actual stuff which is correct, but yeah, let's say I figure out R. Okay, if I figure out R, to figure out P, I realize that P is technically dependent upon Q, because obviously P can start off from 0, but then it is technically dependent upon Q. Now you might argue the same thing, that Aryan, R also is dependent upon S. I will say this is the parent, so I can freely move R, and then what I will do, rather than R depending upon S, I will make, okay, S depends upon R. right? So that again, which means that here I have R. I can put inside this one more for loop for S. That now, rather than R depending upon S, ultimately S depends upon R. Same thing, right? Okay, this is sorted. So R technically is sorted. R is sorted. The issue is with P. The issue is with P because P depends upon Q. Q depends upon R. So even if I am good with this term, that I will depend, like I will make my Q depend upon either P, or I can say okay, P depend upon Q. I could do the same thing which I did for R and S by relating P or Q, but the issue comes up when your Q also depends upon R. So technically that's the worst case. So ultimately we realized the issue right now we are having. R and S I will fluctuate, which means I will let them move it as a for loop. And I also realize that R has a limit from 4 to n minus 2. I will move it and I will make S depend upon R, which means that my S will now move from R plus 2 to n. Right? It is perfectly fine. This portion is perfectly fine. But the issue arises that when my P needs to move from 0 to Q minus 2, but then the Q also was having an issue that it will move from P plus 2 to less than equal to R minus 2. If this is happening, good, which means that I can relate this loop. Okay, let's say R is my parent loop, parent for loop. Inside that R, I can have a S for loop. Okay, that's also perfectly fine. But now my P cannot directly depend upon R, which means that I am saying that I will have one more for loop where the Q will start off from some value. Again, the value will be 2 in this case, as you can see, 2, and will go up till R minus 2. And then inside that a for loop. So technically I was able to achieve a O of n cube solution now. But ultimately we saw that we have to get the O of n square solution. So somehow I have to get rid of this, or maybe find some relation that I have to get rid of this. How I will do it? Okay, let's see. Now imagine, again, so far keep on imagining until unless I will tell you to imagine. Imagine that you fix again. Right now you know that your R is the driving factor, which means you have to go ahead along with R. So imagine for a specific R. Imagine for a specific R. Your ultimate maqsad, as you are trying here, what you were trying by having this P and Q relation, what you were trying to try for all possible PQ pairs. That is what you were trying, right? For a specific R, you were trying for all possible PQ pairs. That's what you were doing. So ultimately, I know for a specific R, I was trying for all possible PQ pairs. That's what I'm going to tell you right now, that how this we can achieve in just O of n time. Let's see how. So again, I make you imagine that, okay, my R is fixed. If my R is fixed, and let's say again, I'm not taking the distance, like the actual distance in consideration, which means if you remember, the distance actually should be following this specific thing, right? But let's for now, to just showcase, I'm ignoring this distance thing. I'm just keeping sure that, okay, P, Q and R are kind of in the order, which means P is less than Q is less than R. The actual distance we will see in the code itself, but right now I'm following this just to explain that how I will find all possible PQ pairs in as less time as possible. Okay, you know that you know that R was fixed. What I did was I fixed Q also. I fixed Q also. So what I said, Q will be nothing but R minus 2. Again, you see that I fixed Q also, although it is kind of violation of what I wanted, because I want to try for all possible PQ pairs, right? But here I'm saying I fixed Q. If I fixed Q, then only P will move. Only P will move. Okay. So technically you covered all PQ pairs such that your Q is fixed, but P goes from here, then here, then here. Now you might argue, Aryan, okay, technically you covered all possible PQ pairs, but not all possible, because you did not consider the PQ pair when the Q would have been here. Obviously, yes, you are true. You are correct. Which means that I will cover this pair when my R would have been fixed here. When my R would have been fixed here. Because obviously I told you that, okay, R is fixed. I told you to imagine R is fixed. So when the R is fixed here, I covered all possible PQ pairs like this. When the R is fixed here, then I covered all possible PQ pairs like this. Ultimately, if I showcase, okay, where it is gone? Yeah. Ultimately, if I showcase, if I go back a bit step backwards, then Q will be here, R or P or your P will be here, right? And then R is fixed here. So as I told that R is moving forward every step, that R is moving forward every step, which means because R is moving forward every step, and also I am fixing my Q as just one step before R, no matter what, I am trying all possible pairs, not for a specific R, like for a specific R, again, for a specific R right now. You considered one P, another P here, but one more pair, which was PQ, was already covered in the previous iteration, right? And same way, all possible PQ operations where P is here, Q is here, P is here, Q is here, would have been covered, like for this specific R, all possible other iterations would have been covered in the previous step. For this, all possible iteration would have been covered in the previous step. So you see that I am accumulating those things and I'm not computing them again and again. That is how, again, rather than shifting my queue again and again backwards, as in like trying for all possible queues, I fixed my queue, because for all other possible options, I can take the help of my previous step. Thus, I will not be computing again. So what did I do? Like, what did I do here? I did one very basic stuff, that I fixed my queue. Rather than moving my queue, I fixed my queue. If I fixed my queue, now my R will be dependent, sorry, my P will be dependent upon only R. So now this for loop will not be required. I can move my P on the basis of my R only directly. Thus, I should be able to achieve O of n square as a time complexity. And how I did that? I simply made sure as my R is moving, I'm accumulating the result as of what I have got. But now you might ask, Aryan, okay, that seems pretty decent and okay, things look good also right now. But where was the maqsad? Like, where's the problem gone? Technically, yes, the problem we have actually missed. What was the problem itself again? Let's see, before going on to that, let's see what we have found out. We have found out that we will be able to achieve all PQ pairs because of the above strategy. And also, as I showed you that with this strategy, that for a specific R, you are going to try to like going and trying for a specific P, this will give you all PQ pairs, and these two, which means this one and this one, will give you all RS pairs. So technically with this you got all RS pairs, with this you got all PQ pairs. So now you have all PQ pairs, you have all RS pairs. So now you have a relation between PQ, you have a relation between RS. But your equation which you wanted to have was nums of P multiplied by nums of R equal to nums of Q multiplied by nums of S. But now you know that you have relation between PQ and RS. So let's bring them together, PQ and RS. If I brought them together, I also know that I can cover all PQ pairs, which means I know the corresponding count of it. I know the corresponding count of all such n like nums of P upon nums of Q pairs. I know the count. Then I can count this also. Now, what you mean by count this also? Let's simplify this problem and let's imagine that I will redefine a bit and give you an easier version of the problem. So rather than giving the ratios and comparing them and being equal, imagine rather than having 4 indexes, you had 2 indexes, I and j. And if you have 2 indexes, I ask you count the number of pairs ij such that nums of I is equals to nums of j. Which means now your problem resolves to count the indexes ij such that the nums of I, nums of j are equal. So if I give you this specific input, right, in which you have to find all such pairs, where the value is same. As you can see, if my I is here, j is here, that is one such pair. I is here, j is here, that is one such pair. Now, very naive way to implement this will be, to try for all possible ij pairs, like this. But obviously I don't want that. How I will do it? I will simply iterate from left to right, and I know for a specific j, to make a pair, I should get how many 2's are there previously. So what I did, I maintain a hash map of 2. So in the very beginning, again, this is a very basic problem, right? In the very beginning, I am at this location. If I'm at this location, I know that, okay, the count of 2 is this. To make a 2-2 pair, again, my maqsad was to count the number of 2-2 pairs. To make a 2-2 pair, I know, okay, I have no such 2 present before. So, okay, no pair can be made. So, okay, let's say I find number of 2-2 pairs. So far it is 0. Okay, no worries. I will move on. Let's say move on. Okay, move on. Now I found another 2. Okay, but as I moved on from here, I also made sure to increase my count of 2. Okay, now for this specific 2, how many pairs I can make? I can simply refer how many counts of 2 I had previously. This will give me number of pairs I can make. I can make 1 pair. Okay, I will simply say number of pairs can be made as 1. Okay, I will move on next. But before I move on next, I will increase the count also 2. Now for this specific index, how many pairs I can make? Obviously, I can make 1, 2, 2 pairs, which is the specific count of 2s previously. I will increase the count by 2. Okay, now move on next. Okay, move on next here. It is not to move on next here. Now, but as I move on next, I should increase also my count. Now, as I reached here, how many pairs I can make? 1, 2, 3, which is the count of 2s previously. Okay, simply add a 3. So total count of pairs which I can make for 2, 2 will be nothing but 6. How did I find that? I just simply found that by simply iterating and maintaining a hash map for the same. Now, what is the hash map? Hash map contains the value, which is this specific value, which I was trying to find. You know, nums of I, nums of j, right? This is nums of I value. This is nums of j value. Cool. In this case, what will be the, again, if you remember, this key, what is the key? Key is nums of I itself. If I ask you, if you want to do the same thing in this approach, what will be the key? Key nothing will be nums of p upon nums of q, and do the exact same stuff as what you did. This is your corresponding key, right? So I can replace and say this is nums of I. This is my nums of I. And obviously, this is corresponding to my nums of j, which is nr upon ns. And that is how you will achieve it. Now, if I show the corresponding code, that's the ultimate maqsad for us. Let's see the code. It's pretty simple. Firstly, I maintain the hash map. My hash map will have a key. If you remember, key is nothing but the ratio. Key is nothing but, again, I will tell you this is actually a bit wrong in terms of edge case, but yeah, this is the key for us, right? For my hash map. So I'll come on back. I'll say this is corresponding key, which is double, which can be a ratio, and the count for it. I will iterate from the possible values of r. Then I will fix my q. I told you why we fix the q. Then I will be easily able to iterate on the all possible values of p. Now, because p is q is fixed because of r, so p only depends upon r. Same way, s only depends upon r. Now, this is for my key, which is np upon nq. I made the key, which means the key will be nothing but this thing, np upon nq. This is the key. Simply update the corresponding count of it. Update the corresponding count for it. Now, when I am at the actual location, which is ns upon nr, when I am at it, I know this is nums of j. So make sure to add the corresponding count for it, as what we saw. Again, this ratio can be confusing, so always relate this with a simple example like this. Cool. So I will simply add the corresponding count which I got from above, and ultimately getting the corresponding answer. Now you see that I have got the keys as a decimal. Now if you don't know that the actual decimals have a very big issue of precision. So there's a possibility that, okay, 3.336 is not equal to 3.3359, right? So this can give me an issue. So in this scenario, rather than building a key with the actual result of the decimal, which means that if I have a decimal, if let's say I should say my value is nothing but, let's say, 9 upon 6. So rather than actually building the corresponding result for it, which is the corresponding answer, 1 point something, and what if 3 upon 2, it is also 1 point something. So what we do to bring this specific, again, rather than converting this actual fraction to a decimal, I convert this fraction to its lowest possible fraction divisible form, which means that lowest possible, that it cannot be divided against each other, so that I can build a key from it. What I mean by building a key from it, here I have 9 by 6. It can be divided more. as you can see, I can divide both by 3, right? Now, this is the last thing, last possible result. I cannot divide this by any other thing. So any result whatsoever, even if let's say this would have been 18 upon 12, anything I should bring them back, or I should bring all these fractions to its lowest possible form. What is this called and how it is achieved? Simply, this is achieved by dividing both the numbers with its corresponding divisor, or I should say factor, which is called as greatest common divisor. So I will find the greatest common divisor of both the numbers, which is nothing but 6. I will divide both the numbers by 6, which will give me 3 and 2. Now this is the ultimate ratio. Again, make sure to not convert this to a decimal. The actual key will be nothing but 3 hyphen 2. Again, convert this to a string, hyphen, add a hyphen, convert to a string. So this is the corresponding key. And this key will help me to not convert the actual ratios to a decimal. And this is the only change which I did in an actual step. Here you will see that here I converted nums of p divided by GCD, adding a hyphen, nums of q divided by GCD. Same way, nums of s divided by GCD, hyphen, nums of r divided by GCD. If you don't know, Java doesn't have a GCD function, so you have to find it by yourself. If you don't know what GCD is and how to find it, just write GCD by Aryan Mittal. You will get the video. Just watch that video and you will get it sorted. But in C++, we have underscore GCD, so we can use that inbuilt function to get the answer. Cool. I hope you guys got it. Again, the only fact here was just to understand this thing, this specific strategy and getting this thing sorted. That is the reason this problem had a lesser success rate and was much harder than the hard problem. Cool. Bye bye. Take care. If you liked it and want to watch more such videos, keep up my motivations so that I can make ones. Please like the video and comment down below what you liked it, or if you don't like it, just dislike the video. Bye bye. Take care.